Today specifically we're going to talk about the addition of vectors, and I want to give you a set of steps on how to do addition of vectors. And because this class did a little bit of work on Friday, we're going to do one that's a little bit more complicated than the one I started with in first period because they had not started at all. So today we're going to talk about relative velocity for airplanes. Now, I use airplanes because there's some specific vocabulary that you have to know for this, and I want to make sure that you guys know the vocabulary. When we do addition of vectors, the actual process of addition of vectors is actually very straightforward and only has 4 steps. So before I launch, let me tell you what those 4 steps are so that once we get into the weeds of this, you guys can refer to these 4 steps. Step 1 is you need to convert all your vectors to rectangular. And it's important to understand that they have to be the same type. You can only add together vectors of the same type. So when we're talking about adding vectors together, we need to make sure we're adding all of the same type of vector together. Step 2 is we add together like components. Step 3 is we convert back to polar. Now, I said there was 4 steps, and I only listed 3, and at the end of this, we really have our answer, but there is a step 0 that you have to kind of employ and think about before you do any of the other steps. And that is, you need to have a consistent frame of reference. A consistent frame of reference. I don't list this as a step because it's how you start the problem. So although there's 3 things that you have to do to add together vectors, you do have to have a consistent frame of reference or none of this works. And I'm gonna get me out of there because clearly I'm in the way, just in the way. So let's do a sample problem so that we have an idea of what I'm expecting of you. Let's say a plane is flying at 200 meters per second, 40 degrees north of east. And then let's say that there's a wind blowing (100 meters per second) due north. Truth be told, no plane would be flying if there was a 100 meter per second wind, but I just chose easy numbers for us to work with. If there's a 100 meter per second wind, the plane would be in a hurricane and probably would be unable to do much of the whole flying thing. Now, when I say we have to have a consistent frame of reference, I've provided a consistent frame of reference. I am using north, south, east, and west. And because of that, I've given a consistent frame of reference. The sum of these 2 things would give us what we call the ground speed. The ground speed is the speed and direction of the plane relative to a fixed point on the ground. That's why these are called relative velocity problems. They are relative to a fixed frame of reference, an agreed upon frame of reference. So when I talk about the flying of the plane can point itself and fly however it wishes. but the air in which it's moving is also moving along with the plane. So the plane's actual progress relative to the ground is affected by the wind. That's why we needed this fixed point of reference. Ground speed is the fixed point of reference. The ground represents a point that is not moving relative to the wind, and therefore we use that as our fixed point of reference. In doing these problems, I always want you to sketch a quick diagram of what's happening. And it doesn't matter which vector from which you choose to start. I want you to depict the two vectors in as accurate a way as possible, which is why I asked you guys to take out a ruler. Because if nothing else, 200 is twice as big as 100, so you should be able to make up a relatively straightforward and reasonably sized answer. This is all taking place in the first quadrant. So I'm going to shift my origin down to the bottom left, and I'm going to put north and east here. Although it doesn't matter which one of these you choose to do first, I always draw in the ones that are in order. So I'm going to put the plane in first, and I'm going to choose to draw a line. I'm picking the length of this line arbitrarily. You guys have a ruler, so pick something to which you can make another line that's half as big and still be able to clearly see it. So it says it's 40 degrees north of east. This phrasing might be new to you. 40 degrees north of east means face east and turn north 40 degrees. That's telling me where to put the angle. That's critical because if you get that part wrong, everything from this point forward will also be wrong. Now the next one is easy. I did that on purpose. It's 100 meters per second due north, so I'm going to draw another arrow. Due north, and I'm going to do my best to make that arrow's length half the length of the plane. Now the wind is 100 meters per second and the plane is 200 meters per second. When you're done, the line that connects the origin with the end of the last vector is the resultant. For this problem, the resultant would represent the ground speed of the airplane. Now, we did a similar problem to this on Friday. So my expectation is I can stop talking right now, and in a few moments, I should be able to get from you guys the length of the resultant and the direction of the resultant, because we did this on Friday. So I'm going to stop talking now, and I'm going to give you guys about 3 or 4 minutes. You're welcome to chat it out if you wish, but I think most of you can do this. That's the first thing I would tell you to do. But that's not going to solve the question. To solve the problem, you have to do all 3 steps. Convert everything to rectangular, add like components, and then convert back to polar. But before you do that, we need to choose an adequate frame of reference. That might be more complicated than it appears. It means I have to choose what I call positive and what I call negative. So though it seems like a minor thing, I'm going to choose downward and to the left to be negative and upwards and to the right to be positive. Next, I need to take each of my vectors and convert them to rectangular coordinates. Now, the wind doesn't really need any conversion because it's due north. It's pretty easy. So when I say I need to convert them, what I mean is you need to find the x and the y component for each vector. The wind doesn't have an x component, so it's just 0 and 100. But the plane does. So in order to do the plane, I need to look at the plane by itself. So for 153.2, 128.6. Any question about where I got that from? Now, all that's necessary, add like components. So 153.2 here, because it's just adding 0. But the next one is going to be 228.6. Now this is the sum. It is the ground speed. But it's in rectangular form. And my answer has to be in polar. So to find the polar answer, I need to convert this by drawing a triangle. These represent the opposite and adjacent for a triangle. Directions over here said go 153 in the x direction and go 228 in the y direction. They were very clear, and so I'm going to get another coordinate system here, one free of distractions. And it actually doesn't matter how you draw this. I'm going to purposely draw it in a way that I think you wouldn't do it. I'm going to draw the 228 first. And then the 153. It doesn't matter what order you choose to put your vectors in. They're going to be perpendicular to each other because one's in the y direction and one's in the x direction. You simply need to make sure that you get your angle correct and name it relative to north, south, east, and west. So I've chosen to put the triangle like this. The resultant starts at the origin and is drawn to the tip of the last vector. You need to figure out this angle, but more importantly, you need to be able to figure out how to express what direction it is. So we'll talk about that tomorrow. We were working this one more or less together, but at this moment, I want to stop and say, look, I need you guys to figure out what the angle is and what the hypotenuse is. And if I didn't say a few of these things yesterday, I would like to finish them off. I would like to remind you that when I drew this 228 in and I drew this 153 in, I was following the directions that were given to me. It was follow those directions. So you have 60 seconds, and I'm going to call on 3 of you. One of you to give me what r is, one of you to give me what theta is, and then one of you to give me the reference. Something with north, east, south, and west in it. 60 seconds. All right, so 275 meters per second. Fantastic. So then I want to draw this fancy upside down division symbol. That's the way I like it done. And let's see. Emma at home, can you give me the angle?
I got around 34 degrees.
34 degrees, sounds about right. And let's see, can somebody else from home, and I'll let it be anybody, can you give me the rest of it, the blank of blank?
Is it east of north?
It would be east of north, thank you. That's what I expect you to do first 10 minutes of class tomorrow. You'll take two vectors, add them together, and produce a resultant vector that is in polar notation with all of those characteristics. The size of the vector, the angle, and how to represent the relativity of it. Yes, sir?
Would it also be acceptable to say like 56 degrees north of east if you want to do this like keep it consistent?
It sure would be. And there'd be nothing wrong with saying it. Those are the exact same thing. In fact, you could also say 56 degrees from the positive x-axis. All of those are fine. The problem with this one, of course, is as you know, if you have any in the second or third quadrant, you're going to get relatively big angles. Not that it matters to me, but all I need from you guys is to ensure that you are providing proper reference for your vectors. And I don't care what that reference is. So, remove all distraction. Now I'm going to look at the plane all by itself. And for some of you, doing it this way might seem like a lot of work because you're taking up all this extra paper. But until you're proficient at this, take up the paper and do it right. Take some time and draw it separate so that you don't get confused. Otherwise, you're just going to look like you're not capable. So 40 degrees and 200. The components are a right triangle that's wrapped around the angle. I'll say that again. When you're drawing in components, they represent a right triangle that is wrapped around the given angle. You are creating a triangle. That's what components are. They complete the triangle that is suggested by the resultant. So I have created this triangle from the vector, treating a vector as a resultant. From the way it's drawn, this is the opposite side and this is the adjacent side. So I will use my SOHCAHTOA. Sine of 40 is opposite over 200. Cosine of 40 is adjacent over 200. And that's really all I need. I can write out tangent, but I don't need it. I would only use it to check my work. So I'm skipping some of the steps from looking at triangles because I'm assuming you guys are making yourself proficient. The opposite side is going to be 200 sine 40. And the adjacent side is going to be 200 cosine 40. Ashley, what's 200 sine 40? I know you have it. 100 what? Thank you. And can you tell me the 200 cosine 40? Thank you. So those are the lengths of the two components. Now what that really means is 153.2 x hat plus 128.6 y hat.